space of compact metric spaces.
Yes, okay, so let me rephrase the question. For example, if we talk about stochastic processes, then there's tightness, which is the abstract thing, and then you have to check that the finite, all finite dimensional marginals have the...
Exactly.
Okay, so what is the...
Okay, if you want the analogous of this is a very, very good question. In fact, you must be given a candy. If no caipirinha, but a candy first. So this is really a good question. If you want to have an analogous of the finite marginals in the Gromov-Hausdorff sense, then what you need is basically you take endpoints in your space. Well, yes, if you want, or fixed, it's the same. But say randomly to simplify the things. And now you want to understand what is the matrix of distances between these 2 points, these endpoints. And if you can identify this, then your space is totally characterized. Okay, so this is an analogous. So in the case of stochastic processes, indeed you can identify the finite marginals. In our case, you can do that. There are also other characterizations, but this is one good characterization indeed.
And as far as I understood, they identify the 2-point function?
Yeah, two point. You had a theorem. For the 3-point function, you will have a very nice, a wonderful, an amazing tutorial at the end of the week, which will deal with the 3-point function. But I won't compute the 3-point function, but I will give you the main ideas. Hi, how are you? You're a bit late.
I know. I was at the loss.
Okay, and okay, 4 points we don't know, okay. So 5. Okay, but you will see that we still have some very nice properties that are shared by all the limiting space. Other question? Yep.
Greg said today that when he said show that the distance is less than v of a side.
Exactly. This is the first picture of my blackboard. Do you want me first? Maybe.
So could you complete the question?
Exactly. So let me first remind you of the bound that Gregory did this morning. He was doing the bound right here. You remember here. But now I will do it here. So don't get confused. So the thing is to understand the distances between 2 points. Say this one and this one. Well, you could say, well, I will construct the whole quadrangulation and then compute the shortest path, and then I will have the exact distance. Try to do it. Okay? But if you only want a bound, what could you do? Well, you could say, I know that there will be a path from this -7 to the root of my quadrangulation. The path goes as follows. You know that with the Schaefer bijection, the -7 will seek for the first -8, this one. Then this -8, you do the contour, and as soon as you find the first -9, this -8 is linked to this -9. You go on, you do the contour, till you find -10, which is here. So -9, -10. Okay, let's go a little bit quicker. -11. 11, there is no 12 except here. Okay, so I do this, and I'm on -12. And now I say that I could do the same thing starting from this -6. So this -6 will look for the first -7, which is here. This -7 for the first -8, -9, -10, -11, and then -12. And now you see that these two paths, they merge. Actually, they merge at this -12. What is this -12? Well, it's a -12, but more important, is that this minus 12 is the minimal label between this minus 7 and minus 6, which is minus 11, minus 1. Because if you think, let's say, 10 seconds, you know that if you start well, this red path is called the maximal geodesic, just to give a name, maximal geodesic. So this maximal geodesic will look for the minimal value of a label between, well, in this part of the tree, okay, which is minus 11. Then this minus 11 will look for the first minus 12, which is not in this part. So here, in this part of the tree. Now, if you do the same starting from this minus 6, I can assure you that these paths, they will merge at the first minus 12. Because this is the first minus 12. So starting from minus 6, you go down, minus 6, minus 7, 8, 9, 10, 11. And once you reach minus 12, this is the first minus 12 in this contour. Okay? So these two paths, they merge at this minus 12. Now, well, look, I have an honest path that goes from this vertex to this one. Just follow the red path here till you reach minus 12, and then go backwards till you reach minus 6. So what is the length of this path? Well, it's exactly minus 7 plus minus 6 minus 2 times the minimal label here, which is minus 11, plus 2. So this is an illustration, an example of the bound, which is trivial. You can see by yourself. It's trivial. You just take two paths, and then they merge at the first occurrence of the label, which is the minimal label between the two in the contour, minus 1. Does it answer your question, Leo? No. Well, okay.
So then, Greg said that this function, the label plus the label minus twice the minimum plus 2 defines a pseudo distance, so it encodes a tree.
Indeed, indeed.
You should think about what this tree is.
And you want me to give you the answer, so that you get a Gandhi by Gregory.
No.
Okay, this tree is called the geodesic tree. It codes all the maximal geodesics in the tree. This is a branch, this red thing is a branch of the tree. This one. And this other geodesic is another branch of the tree. And at this point, they merge and they become, till you find the minimal label in all your tree minus 1, which is, this extra vertex that you put aside. Okay? So you can check, find out by yourself that this tree is the geodesic tree, formed by all the maximal geodesic till they merge. Okay? Other questions? Okay, is this bound clear? Okay, just maybe this one only look at the picture, but if you want to do a lower bound this time, well, the joke is lower bound. Well, maybe I should not go into details, but look, take this minus 9 in the geodesic path between this minus 7 and minus 6. Minus 9. Now, this minus 9 has at least 2 corners, one here and one here, since is a point on the geodesic path between 2 points in the tree. Okay? So this minus 9, you know that from this corner, there will be a path, an arc, to the first minus 10. Okay? Now, after minus 10, minus 11, minus 11, 12, and then go on. Okay? And now, from the other side of the minus 9, you can start the same procedure. Minus 9 will seek for the first minus 10, which is here, then minus 11, and after some time, they merge. Okay? So you create a cycle a yellow cycle that I hope everybody can see, separating this -7 from -6. Okay? So you can be sure that if there is a path in the map going from this -7 to this -6, this path has to cross the yellow cycle. And the yellow cycle, as you can see, only has labels which are less than -9. Okay? So in other words, if you want to go from -7 to -6, you have to go down below -9 before going up to -6. So the distance between this -7 and -6 is at least, well, 2 plus 3. Okay, that's it. Just to show that you can have lower bounds, which are a little bit more complicated, but the upper bound is trivial. You have to be convinced that the upper bound is trivial and that this upper bound actually gives you the tightness argument. Nothing more than that. Well, yes, I should admit that there are technicalities, but in the spirit, there is this bound, and that's it for the tightness. Okay, other question? Otherwise, the tutorial is finished. You can okay? No more question on maps? So the goal of this tutorial, forget about maps. We will deal with the Brownian continuum random tree, the CRT, and we will introduce, okay, remember the very first tutorial when I was still 24 years old. We saw that you can actually construct, I don't know if you remember the Cayley tree, which are trees in the graph theoretical sense with labels out of a Galton-Watson tree conditioned on having n vertices, and this Galton-Watson tree is a Poisson of parameter 1 Galton-Watson tree. So we will use this construction. So we will, with the help of the Cayley trees, we will try to understand what is the scaling limit, the structure of large Galton-Watson trees. And I tell you that Galton-Watson trees, Poisson, geometric, whatever, if they have a finite variance, then they converge to the Brownian continuum random tree. So this procedure will give us a way of, well, understanding the limiting object. So it starts with the Aldose-Broder algorithm. And the Aldose-Broder algorithm is, well, one of the way of sampling uniformly from the set of spanning trees of a given graph. So here is a given graph, not necessarily planar, but, well, here it was the case for the picture. And we want to take uniformly at random a spanning tree of this graph. So you can be convinced that there are a lot, many spanning trees of this graph. So you have ways of computing this number, but how can we, well, sample from this set without basically knowing it? This is the Aldose-Broder algorithm. Wow, you took exactly the same tree. Let me add an edge. -7. Yes, Balash? You just have to read the sheet and do the first question. Sheet number 3. So I'm a bit quantic particle. I move from the...
Special case of Wilson's algorithm? Or?
No, okay. Wilson's algorithm is more efficient, but for the purpose of this tutorial, we really need to rely on the Aldose-Broder algorithm, which was discovered first, before the Wilson algorithm. Wilson algorithm that you saw in Vincent Beffara's course is very well suited for the analysis of the Louperez random walk, but not for the study of the CRT. Three. Sheet number 3, called Aldose-Broder algorithm and stick breaking construction of the CRT. Not the 6th one, but number 3. It was on the previous exercise sheets. Exactly. The title is Stick Breaking Construction of the CRT. Before number 5, number 3. And tomorrow or Wednesday, we'll do number 4, and then switch to number 6. So the algorithm goes as follows. You start from any vertex in your graph. Say this one. Well, not this color, this one. And after that, you do a simple random walk. That is your, simple random walk. You all know what it is. You do a simple random walk on your graph. And each time you visit a new vertex, you add the edge through which you've been to meet this vertex. Okay, so x0, x1. x1 is a new vertex. So you add this edge. Okay? You go on. x2 is here. x2 is a new vertex in your set of visited vertex. So you add caramba, this edge. Okay? Now, x3 is the same as x1. So no new discovered vertex. So no new edge. Then x4, this is a new one. Then x5, which is x0. So no new visited vertex. Then x6, this one. Then x7, x8, x9, so a new one. x10, a new one. x11, a new one. x11, x12, the same as x9. x13, 14, 15, and 16. And at this point, you have covered the graph. So you stop here, and you look at this blue thing, and this thing is a spanning tree. So first, try to convince yourself that this blue thing is indeed a tree. Yes, this blue thing is a tree. Wow. Yeah, but in general, if the graph is connected, of course. You don't want the candy for that, do you? You do want the candy for that? No way. Just a tree to start with. Spanning tree, it's the theorem just after, which is admitted. In 13 seconds. I want everybody to understand why it's a tree. So, Sean, why is it a tree?
So if you have a cycle, then you look at the last edge when it hits this last vertex.
That's one possibility, yeah. Okay, but something quicker. How many vertices does this tree span? Well, exactly the number of vertices of the graph. Because when you reach a new vertex, you add the edge that you've traversed to visit this vertex. So actually, it's obvious that every vertex except the starting point will be spanned by this tree. Okay? But the root vertex is also spanned because when we start from x0 to x1, we add the edge x0, x1, so all the vertices of the graph are spanned. Okay? So all the vertices of the graph are spanned. Two ends? Okay, thanks. But how many edges do you have? Well, you have, if the number of vertices you denote by n, then this tree has n minus 1 edges. Why? Because each time you encounter a new vertex, which is not the starting point, you add an edge. So you add exactly n-1 edges. So if you have a graph with n vertices, n-1 edges, then, and this graph is connected, which is the case, then it's a tree. Okay? Okay, so we will, for the first part of the tutorial, we will admit that this gives us a uniform spanning tree on the graph. Whatever the graph, and more important, whatever the starting point, which is a bit surprising at first glance. But this is true. And we will focus on the case of the complete graph over n vertices, which is the graph where all the vertices are connected to each other. Well, this is the example with 5 vertices. All the vertices are connected together. Okay? And what is a spanning tree of such a graph? Well, you can label the vertices from 1 up to n. And what is a spanning tree on this graph? It's just a Cayley tree. So a spanning tree of the complete graph Kn is a Cayley tree. So I recall that Cayley. You remember the face of Cayley? The guy with the cell phone. So Cayley tree. So a Cayley tree is just a tree in the graph sense, whose vertices are labeled by 1 up to n. Okay? There is no embedding, no order. Okay, so if we admit that such a device gives us a uniform spanning tree on the complete graph, then this Cayley graph is also uniform. Okay? And just to explain you the motivation, so we've seen that if T is a Galton-Watson tree with Poisson of parameter 1, not Poisson, Poisson. Poisson of parameter 1 offspring distribution. Then, if you take T and you forget the order, T, well, okay, you take T, you label it, labeling, and then you forget the order, then you end up with a uniform Cayley tree, provided you have taken T conditionally on the fact that the number of vertices, the number of vertices of T is n, so the number of edges is n-1. Okay? Uniform Cayley tree over n vertices. Now I give you for free, which is not a piece of cake, but I give you for free the fact that every nice Galton-Watson tree, if you condition it on having n vertices and let n goes to infinity, and you rescale it properly with the square root of n scaling, then this converge to the CRT up to a multiplicative constant. So I give you the fact that T, this Poisson Galton-Watson tree condition on having n vertices. So you take this tree, T, you renormalize it by square root of n. You can see your tree as a graph, so you can renormalize the edge length to be 1 over square root of n. So this converges in distribution as n tends to infinity towards a constant times the CRT. Okay? So a way of studying the CRT passes through studying, for example, this Galton-Watson tree, or equivalently studying Cayley trees, or equivalently studying a uniform spanning tree on this complete graph. Yes? C, no, it's okay. 1/2, 1/2. 2 over sigma square, where sigma square is the variance or the inverse. Okay, but it's deterministic constant. Okay, so the goal of this tutorial is to study properties of the CRT via studying uniform spanning tree or on the complete graph. So first of all, we will try to understand the first branch of the uniform spanning tree. Because imagine that we start on the complete graph, say we start at vertex 1, and what will do our simple random walk? So, well, maybe it starts at 1, then go to 100, then 200, then 37, and since if you don't eat your past, then, well, you see that you're creating a branch. Well, maybe it's a pictorial representation, but if you don't eat your past, then you're growing a branch in your spanning tree. And if you eat your past, then this branch stops. Okay? And the first question is to study the length of this first branch. That is the first time when you eat your past. So how does it work? So you've got your complete graph where all the vertices are linked to each other. And say you start at 1, and you want to understand when is the first time that you hit your past. So what is the probability? Okay, for the first step, of course, you won't hit your path. So you go from x0 to x1 without any problem. But what is the probability that at x1, you hit your past? So the only possibility is that, well, you're very unlucky and you've chosen to go back to x0. So what is the probability that at x1, you go to x0? So there is only one edge that is linking x1 to x0. Okay? And how many edges do you have available at x1? You've got n edges. So the probability of going back here is 1 minus 1 over n. Well, 1 over n, sorry. Okay? So, and next time, at x2, what is the probability that at x2 you've been wrong and you've chosen one of the two visited vertices? It's 2 over n. Okay? So that is exactly the birthday paradox. That is, you've got a day, a year, sorry, with n days, and you pick somebody at random, then you pick another guy, then another guy, and you ask for the probability that, the second is not born on the same day, the third is not born on the same day of the first and the second, and so on. And you know that you will need a certain number of people before the probability that two people have the same birthday becomes something, well, greater than 1/2. So does anybody knows what this rough order is? You, for example.
Square root of n.
Well, so even the cameraman knows that this rough order is of square root of n. Namely, you need roughly square root of n people to be, well, not sure, but to have a probability non-zero that two of them are born on the same day. So we'll do exactly the same here. So what is the probability that what I called t, maybe I will change notation, but tn1, which is the first return to the first eating time of our past, what is the probability that this guy is bigger than, say, A? So it's pretty obvious that this probability, well, say strictly, is just the product from I going from 0 up to A of 1 minus I over n. Okay? Because you need at each step to choose a guy which is not, which doesn't belong to your past. Okay? No, I don't want to erase this nice picture. So if you want to evaluate this probability, it's pretty obvious. Take the exponential of sum from A equals 0 to A of logarithm of 1 minus E over n. Okay? Here, okay, let's do something rough, something like the physicist at the first step, and then make it rigorous. Say this is minus sum from A 0 to n of A over I over n. So this probability is of order. So if you sum I from I equals 0 to A, you have something like A squared over 2, which must compete with the n. Okay, to have something non-degenerate at the limit. So it's clear that the good order is not to take A, but to take A square root of n. Okay? well, let's say x square root of n, and a equals x square root of n. Okay, so in this probability, now you can do something exact here by saying that, well, the second order of the logarithm will be of order, the biggest I is a, which is of order square root of n. So square root of n divided by n squared for the second order, which is 1 over n. And you've got something like square root of n bidules here. So you've got square root of n plus a big O of 1 over n. Well, so this is exponential minus x2 x squared over 2 plus little o of 1. So this tends, as n tends to infinity, as 2 exponential x squared. Okay? So this exactly tells you that the random variables t and 1, once renormalized by square root of n, they converge in distribution. So t n 1 renormalized by square root of n converge in distribution as n tends to infinity to a random variable r, such that the probability that r is on dx is x to exponential x squared over 2, which is the Rayleigh distribution. Maybe the orthograph of Rayleigh is wrong. Check on Wikipedia. Okay? So here you've got the cumulative function, so the density is expressed like this. Okay, so the first branch of your spanning tree is of order square root of n, and most important, if you rescale by square root of n, the length of the branch converges to something non-degenerate at the limit, which is the Rayleigh distribution. Okay? So if you eat your past, then you will grow another branch. Okay? And the goal of the third question is to understand what is the length of these second, third, etc. branches. Well, I should say this theorem is due to Aldose. Well, not in the Gromov-Hausdorff sense, which is a rephrasing of the theorem, but well, we can attribute the theorem to Aldose. So I give you 5 minutes. It's the same computation. A little bit more complicated, but same computation. You want a candy? Yeah, but you deserve it. Here. You did a great job. You know that with that, in some countries, you could have a PhD. So we will compute the probability, the conditional probability that, well, now we know the good order of the t case, so it's square root of n. And I give you another trick. It's easier to take the square of that divided by 2. So we'll compute this probability knowing t k minus 1 of n and knowing the fact that t k minus 1 is not too big in the square root of order. But this is only technical. Well, and to be even sure that it will work, let's say this, where A and B are positive, like this. So knowing that tk minus 1 is big enough. So at time tk of n, how many vertices have we discovered? Well, not exactly tk of n. Definitely, yes, but depending at time tk minus 1, how many vertices have we discovered? Right, tk minus 1 minus k minus 1. Because at each time we hit the past, well, this the edge that we went through to hit the past won't contribute to a new vertex. So at time, well, maybe there is an error of +1, I don't care. So at time tk minus 1 of n, we have visited tk minus 1 of n minus, well, say k, plus or minus 2, I don't care, vertices. Well, so this condition is just here to tell you that this k is irrelevant compared to this tk minus 1 of n. You have visited much more vertices than the minus k. So the number of vertices that you have visited is roughly tk minus 1. So you were right. But okay, so let us compute the probability. It's the same. This probability is the product from A starting at, well, this, tk minus 1 of n minus k plus or minus 2, up to something we will see later of minus I over n, where the I is the number of vertices that we have visited before. Okay? So, and this thing, let's say alpha n, well, we put alpha n so that alpha n over square root of n squared over 2 minus tk minus 1 of n divided by square root of n squared minus 2 is exactly x. Okay, so we do the same thing. We take the exponential, the log. Okay, we expand the log in the same fashion, I over n, and the second term will be, well, at most, that is where this condition plays a role. The second term, well, the I is at most of order square root of n, because we ask for this one, k minus 1 is of order square root of n, not bigger. And here we ask for something of order square root of n. So the second term will be big O of square root of n divided by n squared. Okay, so we expand the exponential, and we get, so minus sum from this thing to this thing of I over n plus, well, it's a little o, well, it's a big O of 1 over square root of n. Okay? And what were the two bounds in the sum? Well, the first one, with a very French accent, the first one was tk minus 1, roughly, because the k doesn't play any role. It's very, very small compared to this tk minus 1. So the first part here, say inside the exponential, sum from start to end from I over n equals roughly 1 over n start square over 2, well, say end, sorry, squared over 2 minus start square over 2, roughly. Okay? And the end is this alpha n. And we choose exactly the alpha n, such that if you square, you find tk, which is the start, square over divided by square root of n over 2, and you find x. So this is exactly of order xn. Okay? Plus, well, if you want to be very precise, 1 over square root of n. Okay? So at the limit, you let n goes to infinity, and you find exponential of minus x. Okay, so now you can understand why I choose to put the square over 2. It's because we have to compute the sum of the first n integers, and the sum of the first n integers is the last one square over 2. So it's exactly why I did this. Okay, so modulo some technical details which are boring and that I leave in exercise for the tutorial of, I don't know, for the tutorial of Gregory. So this, well, what does it tell you? It tells you that finally, whatever the value of tk minus 1 is, provided it's of order square root of n, then the increments, if you square them and you divide by 2, the increments, they are becoming independent of tk minus 1. You don't have any tk minus 1 in the result, so they are independent of tk minus 1 and distributed according to an exponential. So this exactly tells you that the increment form at the limit a Poisson process of parameter 1. So you look at Tn1 divided by square root of n squared minus 2. Well, say the increment. So minus tk minus 1 divided square root of n squared over 2. This sequence, as k varies, converge in distribution. So I mean that the first k, the first 100 for every 100 converge to the first 100 of this sequence, converge to the standard Poisson point process on R plus with intensity one. Okay, so they okay, clear for everybody? I don't need to. Well, if you want me to do the details, let's see after the tutorial. We'll see. That should be clear. Okay, so I remind you that the Poisson point process is defined as follows. You first sample an exponential of parameter 1 that gives you the first point. Then independently you sample an exponential that gives you the second point. So let's say x1, x2, etc. Okay? So, in particular, you can see, but it's obvious, that the first, well, k1, for the case k equals 1, you see that if you remember this theorem here, this converges to a Rayleigh distribution. So if you take a Rayleigh that then you square, you divide by 2, you find an exponential variable. It's not a big deal. Okay, so at the limit, maybe before I show you how it works, maybe you should try to understand what will be the scaling limit of this process, of this construction of the spanning tree. Is it clear? Something isn't clear. It's not clear. Is it so complicated? I should quit mathematics. Well, how many variables do you have? Tau, x, t. How many equations?
One equation, it's this equals to this.
Well, if you have 3 unknowns and 1 equation, you're in bad shape. I can tell you that.
No, in TNX. You get free inconvenience from having to solve it.
Don't tempt me. It's working. So you know that, well, this, let's denote, okay, tk of n divided by the square root of n, as k varies. This thing converges in distribution as n tends to infinity, denoted by, well, I don't know, little tk. And the tk's is given by tk squared divided by 2 is equal to xk, where x1, x2, xk is a standard Poisson point process of intensity 1. So you don't learn anything if I tell you that if you take a Poisson point process, then you apply a function to it. This function, in this case, tk is square root of 2xk. So if you have a Poisson point process of intensity 1 on R plus, that you send this Poisson point process on R plus by sending x to square root of 2x. And if here the intensity measure is the Lebesgue measure, then here you will get a measure mu, which is the push forward of the Lebesgue measure by this function. And this mu push forward of lambda. If you cannot do this exercise, then you should hang yourself. So you find that mu of dt is exactly t dt. Well, maybe I've made a mistake, so come to see me before hanging yourself. Okay, so this is exactly the same to, if you want to understand what the TKs are, you take a Poisson point process on R plus with intensity T dt. So you have many points as the time grows. So intensity T times dt. Okay, and now, so this is the length of the first branch. This is the length of the second branch, of the third, etc. And we want to understand how the branches are graphed together. But this is kind of trivial. Not kind of, it is trivial. Why? Because, okay, you can imagine that you've got two randomness. The first randomness is telling you whether you're going to eat your past. And the second randomness is here to decide, in the case of you eat your past, which vertex are you going to eat? Okay? So imagine it's trivial. Imagine that at time n, you are going, well, u means the simple random walk. You are going to eat, well, I'm hungry, so I should not say eat. You're going to eat your past. So conditionally on that fact, on that, the point where you eat your past is uniform among your past. Why? So you can, okay, at each time you have probability I over n, where I is the number of vertices you have visited so far. You have probability I over n to eat your past. So first you can decide to sample a coin with probability I over n and 1 minus I over n to decide whether you are going to eat your past or not. Once the result of this coin flip is known, you can sample another variable. In the case of you are going to eat your past, then you sample a variable with which is uniform over 1, 2, 1, 2, 3, 4, 1, 2, up to I, to decide which vertex you're going to hit. Okay? So this statement follows. Okay, so the construction is in the scaling limit. I'm waving hands, but it's not so complicated to formalize. The scaling limit can be described as follows. So you know that these actually are the scaling limits of the length of the branches that you're going to discover with your spanning tree. So you take your Poisson process with parameter t dt. So this is the first branch. First branch. Now, at this point, so you went that way. At this point, you decided to hit your past. And you know that, conditionally on this fact, the point that you choose was uniform. Say this one, uniform. And now, the length of the second branch is given by this segment. So you just graph the second segment uniformly on the past. Uniformly means with the Lebesgue measure. Okay, now this is the third segment. So you were here and you decided to hit your past. Where? Well, uniformly among your past with the Lebesgue measure, say here. Now you graph this little thing. The order doesn't matter because we are considering graphs. And now, arriving at this point, well, it was enough with this branch. I choose to hit my past. Where? Here, uniformly at random. Maybe I should say here. It can be in the branch that you have been constructed here, and you graphed the fourth branch here. Okay, so the recipe is the following. Recipe, graphed a branch at a uniform point on the branches graphed so far. Does this make sense? Okay. So now, if you are a very clever guy, you should nobody's clever. Something is wrong from the beginning. Well, something is very wrong. Something does not turn in the counterclockwise sense. What? But I'm considering a spanning tree on the complete graph, Kn. How many vertices does this graph have? For the cameraman. How many vertices the graph K sub n, n, little indices. How many vertices does this graph have? Kn. How many vertices? The graph Kn. You're diabetic? Well, n. So you've got n vertices. And since the beginning of this tutorial, I've been telling you that, well, the order of the branch is for the square root of n. So this is square root of n, this is square root of n, square root of n, square root of n, square root of n. Well, square root of n is very small compared to n. Where are the other points? Well, they vanished in the scaling limit. They vanished, but not totally, because you could say that you keep doing this construction with all the fragments here. So you've got something like this. And it's not so easy, but it can be shown that this tree, I mean the diameter of this tree, does not explode, does not blow up. So you remain finite So you have something random, of course, but something very arborescent like this. Okay? But this, if I tell you that this is the scaling limit, so this should be the CRT. Something is wrong. Why? Because the CRT must be a compact set. Well, this is not closed. Well, if you know the CRT, you should be aware of the fact that the CRT, the Hausdorff dimension of the CRT is 2, like the Brownian motion. But this is just a union of segments, a countable union of segments. So the Hausdorff dimension of this thing is 1. Something is lost. So you should, if you want to define the CRT in this way, you should take this object that we built from the stick breaking, which is called the stick breaking due to Aldose. You should take this space and take the closure of this space. Because many, many points have been lost. You've got n points. They are in the leaves. They are here. Well, I can make a zoom. Something like this. This is a countable graphing of branches. And you can define the point at the limit here, which is not on a branch. So this point is not in the union of segments. So you have to take the closure to make these points up here. And, well, at least heuristically, it's obvious because we have been considering things at the order square root of n, and we had n points. So we've lost some points, so we have to add them at the limit. And a way of adding them is to take the closure of this space. So I recap. So the CRT. CRT was the scaling limit of uniform trees. Okay, but I told you in the beginning of this tutorial that this scaling limit is, this CRT can also be obtained, as a scaling limit of other Galton-Watson process. Well, provided they have a finite variance. And we considered the Poisson Galton-Watson process. Why? Because the Poisson Galton-Watson process, if you condition it on having n vertices, you label them uniformly at random, then you have a Cayley tree, uniformly distributed. And the Cayley tree can be seen as a uniform spanning tree on the graph Kn. And we had a way of constructing a spanning tree of the graph Kn by this Aldose-Broder algorithm, which, well, you have a simple random walk, and up, you hit your path, you're growing another branch, you hit your path, you're growing another branch, etc. So we had, well, not we, but Aldose had in mind that the scaling limit of this process of growing the spanning tree should converge to a process, and you could define the CRT out of that. This is the case because we completely understood the length of the branches, which at the scaling limit is given by the length of the interpoints of Poisson point process of intensity t times the Liebeck measure. And conditionally on this length, then the grafting point was uniformly on the past, uniformly chosen on the past. But to be proper and to define the CRT, then you have to take the closure of this thing to have the compact metric space that you are looking for. 10 seconds, last remark. This one is not obvious at all. So remember that the CRT, well, maybe 20 seconds. Remember that the CRT was given, well, was constructed by Jean-François Le Gall as the tree coded by an excursion, a Brownian excursion. Okay? So if you want somehow to comment on dit rebondir? To bounce on a question of Balázs, if you want to understand the finite marginals of the CRT, you want to understand what does it give if you take, say, well, 2 points uniformly chosen on the CRT. So you can define that as, okay, you take U1 and U2, two uniform variables over 0, 1, and you, you take the projection of U1 and the projection of U2, and you want to understand what is the distance between these 2 points. So I'll let you think about that, but the subtree spanned by these 2 points is just this subtree that I've drawn in blue in this picture. Okay? Well, it's not, well, it's obvious. Okay, and if you want to understand what is the geometry of this subtree, you want to understand what is the length of this branch, of this one, and of this one. And not obvious, but true, this, well, up to constant, this blue thing is exactly given by this process at step 2. That is, you have a first branch, well, which was, say, this one, and you graft another branch to this one with the stick breaking. This was the first one and the second one. Well, I tell you, and this is true, that these 2 things, they have the same distribution. In other words, the point where you finished your first branch in the spanning tree, this end is a uniform point on the CRT. Well, now let's go to sleep. Thank you. Any questions? You can ask to the cameraman for the birth-death paradox. Fuck.